In this example, we're told we have a total pressure probe inserted into a supersonic airflow. So we'll draw that like this. This is our total pressure probe. So it measures the stagnation or total pressure. And the upstream flow is supersonic. A shock wave forms just upstream of the impact hole. So this is the hole where we measure the pressure. So there's a shock wave upstream of that. And the probe measures a total pressure of 500 kilopascals absolute. So that's the pressure right here. The total pressure is the same as the stagnation pressure. So I'm going to call it P02 since it's downstream of the shock wave. The conditions upstream we'll call 1 and the conditions downstream we'll call 2. So we know the P02 is 500 kilopascals absolute. So that's what is being read from the probe. We're also told the stagnation temperature at the probe head is 227 degrees Celsius. So there's some thermocouple there that's measuring the temperature. It's best to convert that over to Kelvin, so that'll come out to be 500 Kelvin. So you add in an extra 273. The static pressure upstream of the shock is measured with a wall tap. So it'd be like, for example, there was a wall here, and there was a wall tap here, and we measure the pressure upstream. So this is the static pressure, P1, and that's 100 kilopascals absolute. So we're asked to determine the Mach number of the incoming flow, the velocity of the incoming flow, and then sketch the process on a TS diagram. So to determine the Mach number of the incoming flow, what we're going to do is make use of the pressure information. So for example, we're given the upstream static pressure and the downstream stagnation pressure, and I can use a combination of the normal shock relations and isentropic relations to find what that Mach number is. Okay, so let me just sketch this out for you. So we can use P1 over P01, that's an isentropic relation, upstream of the shock. So that looks like that. Of course, we don't know P01 or Mach number 1 just yet. We know across the shock, we can use the normal shock relations to relate P02 and P01. This one is a bigger expression. I'll write it out here, but you can find this, for example, on a formula sheet, or you could find P02 over P01 using normal shock tables. But I'll just write the formula here to be complete. This was actually derived in the lecture material. Okay, so that's how we can relate the stagnation pressure ratio across the shock. Again, we don't know the Mach number 1 and we don't know P01. We do know P1, however. Okay, so you can see that, well, let me put things in terms we know. We know P1 and P02. So let me just write this expression as P1 over P01 times P01 all over P02. And that'll give me P1 all over P02. You see the P01s cancel out. What I'm trying to do is just put it in terms of things that we know, right? We know P1 and we know P02. And then you'll see that this expression is just a function of Mach number 1. Right, so this would be this expression. Let me just highlight it in yellow here. It'll be this expression. So I'll write that like this, just because I'm lazy and I don't want to write the whole thing out. And then we have this other expression here. Let me highlight that one in green. This whole expression is this one flipped over. Right, because it's P01 over P02, and this is P02 over P01, so that's why I have it flipped over. But you'll see this whole thing is a function of Mach number 1, right? So we know the value for the left-hand side. The right-hand side is just a function of Mach number 1. Now, it's a complicated function of Mach number 1, so you're not going to be able to solve that by hand, but you could solve it numerically. Okay, so you could use a root finding method, a numerical root finding method to find the Mach number 1. And so that's what I had done. I won't go through the details of that, but you can use a numerical method, and you'll find that Mach number 1 comes out to be 1.87. Okay? So now that we have the Mach number of the upstream flow, the next thing to do is find the velocity of the upstream flow. So to find that velocity, what we're going to do is just use the definition of the Mach number. So the Mach number upstream is just v1 over the speed of sound 1. Speed of sound is square root of kRt1. We don't know the temperature upstream just yet, but we can find that pretty easily. So in this equation, we know Mach number 1. We're trying to find velocity 1. We don't yet know T1. But T1 is related to Mach number 1 via the stagnation temperature upstream. Right? So here we know Mach number 1. We don't know the stagnation temperature just yet, but the one thing we do know about normal shocks is the stagnation temperature remains a constant across a normal shock. Right? So T01 is just equal to T02, which we do know. Right? So that's 500 Kelvin. So now we know T01, we know Mach number 1, we just solved for that. So we can find T1, and if you plug in the numbers for that, T1 comes out to be 294.1 Kelvin. And then once we have that temperature, we can find the speed of sound up here. And I didn't calculate that one, but we can find that speed of sound. Since we have Mach number 1 and the speed of sound, we can find V1. That one I did calculate. V1 comes out to be 643 meters per second. All right. Now the last thing that we were asked to do is sketch the whole process on a TS diagram. So let's do that. Do that over here. So here's our stagnation temperature, and it's the same upstream and downstream of the shock wave. Our P01, this is our upstream stagnation pressure, we'll put right there. And we're starting with temperature T1, which we said was 294 Kelvin. Notice that that temperature is less than, well, I guess I didn't calculate T2, but it'll be less than the temperature downstream of the shock. Okay, so, and that's because we know the temperature increases across a normal shock. So let me put T1 here, and P1 will be right here. Okay, so that's our condition upstream of the shock. Now downstream of the shock, the temperature increases and the pressure increases, so we'll put T2 there, and the entropy increases, so we'll make that right here. Here's S2, this is S1. So our pressure downstream of the shock is right there. There's our P2. So there's our state 1, here's our state 2, and we draw a squiggly line from 1 to 2 just to indicate that we're going through a shock wave there. When you go through the shock wave, it's essentially a discontinuous process. So we'll just show it as a kind of a jump from 1 to 2. And then from point 2, we end up going, so now we're here, and then to go to the stagnation tube, what we'll do is move isentropically to the stagnation conditions at 2. So here's P02 and T02, so we're going this way. So these are our upstream conditions. We go through the shock wave, the temperature increases, the pressure, static pressure increases, the stagnation pressure decreases, the entropy increases, but we still have the same stagnation temperature. So we go through that shock wave, and then we slow down isentropically to the stagnation port on the probe, which is right there. So this is the probe. All right, so that's the process on a TS diagram. And now I think we've covered everything for this example, so we'll end there.